prediction of thermal profile changes on the heat effective zone during tungsten carbide and nickel composite coating by laser cladding process under different operating conditions. Okay, let's get started. Okay, 2020 since 2021, we have been carrying out the government-supported research project to develop roll coating process and powder technology for manufacturing 1 gigagrade steel plates. As you can see, this figure shows the continuous casting process in a steel mill. The continuous casting is a process of solidifying refined molten steel to make slabs. Refined molten steel is supplied to the mold from the turn dish, and solidification starts from the surface of the slab in the mold. The slab, exiting from the mold, still has a liquid full inside and cools by support rolls and spray coolers to complete the solidification. Since these guide rolls are used in high temperature and high humidity environments, both high corrosion resistance and high wear resistance are required. These rolls are currently coated with the submerged arc welding because the price is cheap. However, in order to produce high quality steel plates such as high strength steel plates, we need a highly functional coating technology using laser cladding process. Okay, as we know, laser cladding is a directed energy deposition surface treatment method that is a kind of additive manufacturing. Laser cladding shows a dense microstructure and has good metallurgical bonding with the substrate compared to existing other surface treatment technologies such as arc welding or thermal spray. So, laser cladding is used in various industries, including steel, automobiles, aerospace, chemical machinery, and so on. On the other hand, practical use of laser cladding encounters difficulties in quality control. During the laser cladding process, a laser beam is irradiated to the surface of the substrate, and then the alloy layer formed between the substrate and the powder is rapidly heated and cooled. The melting and solidification of the melted fuel results in the rapid temperature change in the heat effective zone. As a result, pores, cracks, and thermal deformation can occur. So, the accumulated heat in the heat effective zone must be properly controlled during the laser cladding process. However, previous works on the laser cladding process control have mainly developed the reactive control methods, which have limited ability to respond effectively to troubles caused by the accumulated heat. So, this study proposes a deep learning model that can predict multiple thermal profiles so that it can forecast the temperature distribution of the next state and respond in advance. In the case of laser cladding, as the process progresses, overheating causes thermal distortion, cracking, and excessive dilution in the heat effective zone. In order to prevent these quality problems, it is important to be able to control the thermal profile in the heat effective zone. In other words, quantitative analysis of the heat effective zone is necessary for the quality control during the laser cladding. In addition, the thermal profile of the heat effective zone varies depending on the chemical components of the substrate and powder process conditions. So, in this study, we first quantified the temperature distribution around the laser beam and the behavior of heat effective zone over time during the laser cladding using a thermal imaging camera. And then, deep learning was used to predict thermal profile images of a laser cladding process under different operating conditions. Okay, in this study, S45C steel was used as the substrate materials, that is to say base material. The chemical composition and mechanical properties are similar to rolls in the continuous casting, and the cost is cheaper than existing base materials as CM440. The size of the specimen was set to 100 mm in width and height and 20 mm in thickness. And then we used tungsten carbide and nickel-based alloy powder manufactured by Metco. This powder mainly consists of 60% tungsten carbide and 40% nickel. The nickel metal has lower mechanical properties than cobalt, but has excellent corrosion resistance and oxidation resistance. The laser cladding machine consists of 10 kilowatt laser oscillator manufactured by Laserline and the powder feeding system manufactured by GTB. This machine is being operated by corporation in South Korea. Okay, this figure at the right top of this slide shows the real-time monitoring system for laser cladding. The thermal imaging camera was located within 1 meter of the base material in a straight line and was set to so that the area of interest was not obscured by the laser arm during the laser cladding process. Okay, the laser cladding works were performed after preheating the specimen to 300 Celsius degrees to reduce the incidence of pores and cracks caused by the temperature difference between the base material and the laser. The direction of laser cladding movement was from left to right, and the entire surface of specimen was coated starting from the upper left corner of the specimen. Okay, deep video prediction has made incredible progress in the last few years. SimVP stands for simpler yet better video prediction. Okay, you can see the final preprocessed thermal profile image in this slide. The picture on the left side shows the temperature distribution when the first bead was clad, and the picture on the right side shows the temperature distribution when the last bead was clad. As the laser cladding proceeded from the first bead to when the last bead was cladding, the temperature distribution of the substrate had changed. Even under the same process conditions, the temperature distribution of the substrate increased from about 250 Celsius degree to 450 Celsius degree on average. Also, it can be seen that the size of heat affected zone increased due to the accumulated heat from the previous bead. The temperature of the heat affected zone increased by more than 50 Celsius degree, and the width of heat affected zone increased about twice from about 8 mm to 15 mm. Okay, the evaluation results for single plane prediction is mean absolute error 2.0 Celsius degree. This is a very high prediction accuracy considering the average temperature and the maximum temperature of the heat affected zone. We can compare the actual image with the predicted image as an example. The figure on the left side is the real image, and the figure on the right side is the predicted image generated by the SimVP laser cladding model. The entire coating layer and the shape of the heat affected zone were accurately predicted without blurring boundary of the image. On the other hand, it is necessary to get information about multiple future states for effective control in the model predictive control. So, we conducted an experiment on multiple frame prediction of the thermal profile. First, we calculated the maximum number of time steps that can achieve stable prediction accuracy, even if a prediction point is far away. So we set 10 Celsius degree as the tolerance for prediction error from the interview with experts operating laser cladding machines. As you can see in this figure, SimVP laser cladding model can predict up to 37 frames within the tolerance. However, The mean absolute error increased rapidly after 30th frame. So the experiment was conducted by training the proposed model to predict only up to 30 frames for the stable prediction accuracy of the model. This figure shows the mean absolute error trends for the entire coating layer and the heat affected zone within 30 frames. The mean absolute error trends for the entire coating layer differs from that of the heat affected zone. As the number of time steps increased, the mean absolute error for the entire coating layer increased from 2.52 Celsius degree to 3.58 Celsius degree. But the mean absolute error for the heat affected zone increased by only about 0.2 Celsius. This evaluation results show that the performance of the proposed model is very good. In this slide, you can see a sample video of flying the thermal profile prediction model developed in this study. The screen is divided in 3 sections. In the first section, during the laser cladding process, a laser beam is irradiated to the surface of the substrate, and then the alloy layer is formed between the substrate and the powder. In the second section, you can check the temperature distribution of the substrate and the heat affected zone measured from a thermal imaging camera in real time. The measurement temperature range of the thermal imaging camera was from 900 Celsius degrees to 2500 Celsius degrees, and the temperature distribution of the specimen was visualized by dividing the temperature range into 100 Celsius degree increments from 900 Celsius degrees to 1700 Celsius degrees. In the third section, the yellow graph indicates the predicted maximum temperatures of the heat affected zone, and the blue graph represents the measured maximum temperature of the heat affected zone in real time. There is a time gap between the yellow and blue graphs, because the maximum temperature of the heat affected zone is predicted 3 seconds in advance. Since temp phase to develop a multiple thermal profile prediction method for predictive control during the laser cladding process. The thermal profile prediction model proposed in this study accurately predicted the temperature distribution of the substrate and the heat affected zone. So, quality control is possible by adjusting laser output. So, we can prevent product damage by minimizing the time for which the heat affected zone is overheated. The further research includes 3 items. First, we need to clearly distinguish the area of melt full from the heat affected zone. Second, we need to analyze the temperature change in the heat affected zone according to the laser output. And last, we need to develop a control model that can keep the maximum temperature of the heat affected zone constant. Okay, thank you for listening for a long time. Thank you very much.